there was a problem in the internal database, and it could not be done otherwise. So we are really sending half an hour before because it will be occupied Saturday next week for a master lesson on the games. The presentation of today by Sergio Antares is connected to a visit of 2 weeks. He's doing here at the FISC, so he's a student at the CAI Institute and so the Center of Automatization.
Yeah, it's automatic robotics, yeah, exactly.
And he's actually practically finished his PhD, but still in the independent PhD. He's supervised by Angela Ribeiro and Franco Rippon. And today he's presenting his work on automatic generation of optimized quantum circuits for real-world machine learning.
Right. Thank you very much for the introduction, Roberta. It's a very long title, but it's going to be easier, I guess. So, yeah, this is my doctoral thesis topic that one day I will finish, I guess. So, hopefully soon. So this is the outline we're going to follow in this presentation. First of all, I'm going to introduce a bit genetic algorithms, which I think it's not very usual in physics profiles. So I think it's important. Also, we will go through machine learning just a bit and just commenting how it works and how the machines learn. We will go to quantum machine learning and then how to integrate both things, machine learning, quantum machine learning, and genetic algorithms to optimize quantum circuits. And then we will go through different approaches for different data types. So let's do it. Well, what's genetic algorithms, no? It's an optimization technique that are inspired in biological evolution. Okay. So we have some genetic operators with like selection, crossover, and mutation as the society and all the evolution, Charles Darwin, no? And the goal is to find the optimal solutions for a task, a very defined task, okay? So this is the general scheme that we can get in our genetic algorithms. First of all, we have our initial population, very random population of individuals, okay? And then we have a fitness function in which we evaluate for a defined task these individuals. So we're getting the fitness values are called that we will see later. For instance, in machine learning could be accuracy or complexity of the models and these kind of things. Then we will select the best ones, but not only the best ones, but also some worse ones, because the key of these genetic algorithms are that can get diversity, genetic variability. So we can cross a lot of solutions to get the best ones, okay, at the end. So here we make some genetic operators, such as crossover and mutation, that we will comment later. And it's an iteration until we reach the best individuals. Mm-hmm. If you have any questions, you can ask for sure. Okay. So this is the critical points that we have in genetic algorithms are the genotype. We have the chromosomes. Here also are called chromosomes. And it's very important to define this because it is defining the solution space that we have. And we can explore. We have like a universe of solutions and we can explore it. And then the phenotype is exactly how to decode this individual. So we have the chromosomes, and then we can get a solution, for instance, a quantum circuit in this case. Okay. Here are the genetic operators that, for instance, mutation is just changing some bits. It's a flat bit. And crossover is changing some genes from two parents to get the offspring of the next generation. So I'm gonna introduce, this is if you have any questions about genetic algorithms, we will go through it again. So, but if you have any questions, you can ask, no problem. So I'm gonna comment a bit machine learning. It's a branch that enables to learn patterns from data. We have a lot of data and we can extract information to extrapolate the knowledge to another instances. And there are like 3, 4 now with generative AI, no, let's say, learning. We are gonna focus right now in the supervised learning. I'm not gonna focus on supervised or reinforcement learning, but are important also. So, in fact, reinforcement learning can be used also as genetic algorithms to optimize things. So, how do we learn in machines? Well, this is something that I would like to explain because it's like analogy from our our behavior when we are learning in the university, for instance, and how machine learning models learn. So first of all, we at university are reading and making exercises at class. And then we have an evaluation, exam, no? And if we pass, okay, perfect. If we don't pass, we have to go to study again for the next exam, okay? So the models are exactly the same. We analyze it exactly the same. We have the input data in labels, which is like the books. We have the solutions. Then we have here a model, and here we evaluate the metrics, in this case, accuracy, F1, score, these kind of things. And so when we get the best accuracy or we entrain the models, then we can get a new instance and predict the output. So it's very close to as we are studying, for instance. Okay, so before I said that there are like a lot of algorithms as supervised learning. This is one of the most important ones. It's a kernel trick, it's a kernel method. And also there is a quantum version of kernel method. As you can see here, there are 2 classes, very linearly separable. So it's very easy to identify an hyperplane that can separate both classes into separate places, right? So this algorithm, what it's doing is exactly to locate the support vectors that are these points, very close to the hyperplane, and to maximize the margins, which is the distance between the super vectors and in the hyperplane. So it can be a more extrapolable model. What's happening if we don't have this problem, which is very easy, and we have very mixed data, like this one, which is a Gaussian. So what we are doing is something called kernel trick, and we apply a function to go to a higher dimensionality and to search a linear hyperplane again, like this, for instance, so we can identify the pattern and classify it, okay? This concept is exactly the same one that we are using in quantum kernel method, but this function that we are using in classical machine learning, we use a unitary in quantum machine learning like this. So we have a data encoding in which we embed the variables with some parameters, and then we are using this kernel equation. Well, right now in the state of the art, when we are talking about quantum supervector machines, everybody is using this kind of circuits, which are very like templates, very standard ones. But we were wondering, like, okay, cool, but are always good? Because if we increment these feature maps, when I'm incrementing the number of qubits, when we have more variables, we have more number of qubits, so the expressivity is higher, but the variant plateaus is here again, as yesterday. So we were thinking, like, maybe we can do a fine-tuning of these feature maps. And it's exactly what we were doing in my doctoral thesis. Yeah, exactly. This is in Penny Lane, and Cascade are the feature maps that are used. Yeah.
These are like hardware efficient tools which is suitable for using the simulator.
Yeah. No, I mean in the simulator. Yeah, exactly. Yeah. all what I'm gonna say is about simulations. Yeah, so sorry, I didn't say it, but yeah. So we were thinking about this, and we designed a new global optimization system for quantum circuits. In which the genotype that we were saying before, in this case, we decided to do, it's a binary string, 1 zeros, and the encode a phenotype, which is a quantum circuit. In this approach, what we were doing, it's to encode every single part of the quantum circuit in this string. And it means the structure, I can't move, so I don't stop. So the structure, the gate types, and also the parameters. So we're designing a system that are not based on gradient-based optimization. So what we wanted to do is to avoid barren plateaus with this system. This is the structure, the DNA. It's a matrix with a number of qubits and number of layers that we predefined when we are creating the quantum circuits and the systems. And then each of the all the qubits lines are filled with quantum gates. In this case, each quantum gate is 5 bits. The first 3 bits encode the gate, and the second bits encode the angles. So we have a lot of combinations of it. But we have this operator, which is identity, and R3 because it's a difference, no, it's 8 combinations. Why? Because what we wanted to do is to reduce the complexity, and since identity doesn't affect to the quantum state, it's a way to reduce all the components here. Oh, and yeah, we are using for sure the data uploading, so all the variables can be in more than 1 qubit. So it's a way, yeah.
This secret is containing only these operations, and you can mark it in a line. And the order of the gates.
Straightforward. It's when we have coded straightforward. So if we have this individual is separated in 5 bits per gate. So well, I think there is a better way. Well, there is another image later. This gate is this one, this gate is this one, this gate is this one, and so. I mean, yeah, like you're filling all the qubit lines with every single operators and parameters, so you can get whatever. To be honest. Yeah. Yeah, like the C node are entangling consecutive qubits, and well, I'm gonna say later, but it was like a surprise. But the goal is to make disappear also C nodes to get like a very quantum inspired models. So yeah, the goal is to get quantum inspired in these models. Yeah. Exactly. One string, it's just a quantum circuit that can be a unitary or something like this, and you can, like, with the fitness function, you evaluate it for a task, and then you see if it works or not, and then again, all iteration until you get the best quantum circuits for your case. Yeah. The angles. Yeah. Here there are 4 angles. I know this approach, the first approach we were doing for tabular data wasn't universal gate set, but for the next one, yes, we did it, and we just this encoding is very scalable. because we add more bits here and we have more operators, more angles, and it's very easy to make it longer. So yeah, we did it later, the universal set of gates. So this is the general scheme of the technique we designed for tabular data in this case, but it's general, let's say. We have the initial population, then we split the gates, we get the quantum gates and the angles. We build the unitary as we have seen. Then we compute the quantum kernel. We evaluate the accuracy and the number of gates, the complexity of the model. And then we select individuals, again, the genetic operators, and it's a loop until we reach the early stop conditions that can be, I have reached the best accuracy or the number of generations on the genetic algorithms. So we have like the best quantum circuit for our goal. No? This is important because we are using Pareto front, which is a multi-objective genetic algorithm. It's not one objective, but two. So, well, we have to look to search the trade-off between the complexity and accuracy also, depending on the task for sure. So let's go to the tabular data now that I've presented the machine learning, the genetic algorithms, and the technique we have developed it. So for instance, we have this nonlinear data set, which is moons, very common, I guess, no? And we define this size of the circuit of the evolution with 5,000 generations, 100 population, and these kind of things. This is the scheme of all the algorithm. It's called non-short genetic algorithms too. And well, it's just selecting the population for a new evolution. Here's the mutation, and here's the crossover. That are the genetic operators that we are using in the genetic algorithms in this case. And well, this is the circuit size over the evolution. In the first generations, what we are looking at is this kind of circuits that are very complex. We have a lot of entanglements. It's like very huge one. At the end, we get this circuit with an accuracy of 1.0 in the test set. It means that we are reducing the complexity at the same time that we are maximizing the accuracy. In the unseen data, which is test set, it's not, because if we are using the training set, it's overfitting, doesn't make sense. So this is the way we are doing that. You were just before asking, like this is the encoding part. So this is the string that of our individual. This is the Q0, Q1, Q0, Q1, Q0, Q1, and it's just a straightforward process. Here are two identities and disappear because it makes sense. So this is the way we are reducing the complexity of the solutions. This is another way to reduce the solutions that we are implementing. This is the first generation circuits. And what we want to do is to penalize the appearance of the CNOTs, because in the real hardware, it's more noise and, well, yeah. So what we are doing is to penalize. It's just a size metric. It's the second objective of our genetic algorithms. And the n local, it's just one, okay, one per qubit. But here we have a penalization of 2 for CNOTs. It means that, let's see, if we have an accuracy of 1.0 and we have one circuit with 2 CNOTs and another with 0 CNOTs, we're gonna take the 0 CNOTs because it's much better. It's less complexity and it's the same accuracy. So these are the results that we obtained for the test sets, and we were thinking about how to interpret these results. So since it's a classical simulable and there are no entanglements here, we can take its qubits as a kernel separately and evaluate how it's given the support for the general for the mixed prediction. And here we can see that the first qubit is given just a line because it's one rotation. Here again, and here is some nonlinearity that when we are multiplying all these kernels, we are obtaining the perfect pattern, which I think is very interesting, and it's a line of research, I think, for interpretability of models also. Well, this is validation. We're using more data just to validate the results that work perfectly in these things, and this is the confused matrix we obtained. So, okay, perfect. And so we were working also on real-world metasets. For instance, we can see that all the circuits are classically simulable, more or less. And here, this is a multi-class that we were applying also, but well, I mean, here there were 22 features, and this only are only 8 qubits, which is much better than 22 qubits for processing. So once we had the tabular data, we were thinking about, let's increase a bit the complexity. Let's go for grayscale images, for instance, no? Because images with RGB are more complex to treat. So let's go for grayscale, which is only one band, and well, we can work with it now. Well, this is the thing we were doing for the universal get set. It's just adding 2 more bits, and then we can have all the parameterized rotations. We can have the parameterized rotations, but also with fixed angles. Identities to reduce the complexity, and the synods just to get it. And the angles also we added more with 4 qubits, with 4 bits. So how can we do this? It looks difficult. Like, so we were thinking about a preprocessing step before the encoding of the variables in the circuit. Well, this is just in case, because now I'm going to talk about autoencoders. So before I was talking, and they were saying that they didn't know what it was. So autoencoder is a neural network for density reduction, in which we are training the latent space for, let's say, we are training the model to get in the output the same in the input from the latent space, which is a vector with limited number of variables. Okay, so what we want to obtain for sure is to minimize the loss function when we have the encoder and the decoder from the latent space. So this is a strategy we defined to encode the images in the quantum circuits. We designed the PCA with a number of components, and also Akai, which is a convolutional. Yesterday we had the talk also, the convolutional autoencoder in this case, which is like autoencoder but with convolutional layers, with the pooling, the padding, and these things. And well, we were thinking that maybe defining when we have this model, we have the transfer learning, so we have defined the defined latent space dimensions, so it's fixed. We can't do anything with this, but with the PCA, maybe we could do something different. And what we were doing is to add some bits in the individual to optimize simultaneously the number of components for each quantum circuit. So we are getting a huge system with from the image to the dimensional reduction, and then to the circuit to get the final output with the 1 or 0. I mean, the technique is this part is the same that the other one. Okay. So when we are applying to COVID and to brain tumor, we are getting this these circuits with no entanglements. This is the PCA approach. This is the convolutional autoencoder approach. And we can see that our unitaries and are classically simulatable models in all cases. These are the parameters that we have in the model and the accuracies on average. We're using also the multilayer perceptron just to see that the preprocessing is not doing all the task, because it doesn't make sense. So we are testing these things. And this is the Pareto front we are obtaining, and this is the best individual, which is in this is evolution, generations. This is accuracy, and here we have like a last step. So this is the best accuracy we obtained. And as we can see here, we have a lot of individuals in the Pareto front, very complex and with less accuracy. So when we are getting more in this last part of the generations, then we are obtaining best accuracy and less complex, and better accuracy and less complexity. So we are improving in both cases. So the optimization, the multi-activity optimization is working properly. Now we we increased a bit the complexity, and we went through the RGB images. And again, it's very difficult to put this thing because it's a tensor. There are 3 matrices per image. So how can we do it? No. Well, we were thinking about it, and the segmentation task is something. It's, for instance, a convolutional neural network can take the whole image for processing, and there are very good approaches for classical segmentation right now. SAMI, for instance, in Meta or UNet are used also for these things. So we can take locally pixels from them, and then to analyze the properties of each pixel. And this is exactly what we were doing here. This is the strategy for the information extraction that we were thinking about. So each pixel has 3 properties in these images. It's the RGB, and the binarized image has only 1, 0. So we were thinking like, okay, maybe it's a classification again, but for local properties. No. So, well, here it's important to balance the data set also, because as we can see, the regions that we have in white are very small compared with the black ones, which is the regions that we don't want to analyze because it's the ground. So we have to take into account that we have to balance both data sets to compare them and to get the accuracy, because if not, we have to go through recall, F1 score, and this kind of metrics to get the best. I mean, to not get in overfitting of the models. So we were using these 2 use cases for solar panel segmentations and for cover vegetation. This is the circuit for this segmentation. This is the RGB, which is where we apply this circuit directly. This is the ground truth, and this is the output of the quantum circuit. So as we can see, very fit, so it works. And here it's doing a classification per pixel, RGB. So are the 3 variables, and the target is 1 or 0, which is if it must be segmented or not. No? This is the same, like this is the circuit for the cover vegetation. Here are the metrics, and well, this is the output of the circuit, and this is the ground truth. So we can see that it's working properly. Then we went for another use case, which is the sequential satellite images for yield crop predictions. We have been working until now with more than 1 band as RGB, but satellite images have like 13 bands, which is harder. We were trying to get a quantum predictor for the harvesting of the vineyards, which is, well, the time series was multi-year data. We had like 5 years. The high resolution, well, it's satellite images, so the resolution is very high. It is important to get stable intervals to get the good lags between the elements, because if we don't have it, then we can't take the temporal pattern. And the objective was to predict the NDV index, which is the vegetation index, and it can be seen. It's like this. Okay, so here it's important that yeah. We had the data set with all the images along the time, and we wanted to predict the next step. So yeah, well, I have more slides with this, but yeah, the goal was to predict. Yeah, exactly, the next step. Yeah, it's a regression problem. So this is the strategy we were taking into account to get the step T20. We were, well, this area was very huge. It's satellite images, as you can understand. So we defined some intervals within the images to get balanced information from all the image, because if not, we can't take this properly, and we can have overfitting in some areas, but in other areas, no information, and no. And also, we were getting another filter with all the NDVs range in order to balance all the pixels that we were taking and to train the models properly. So we were taking pixels from this image, okay, with 20 days difference between the images with each pixel, and then we wanted to predict the next one, that we had it, okay? But we had it for the ground truth, to compare. So this is the scheme that we have been seeing. In this case, we are using not quantum supervector machine, but hybrid quantum classical neural networks, in which we had the unitary from this population, but we are measuring, and then we have a perceptron, a linear perceptron, because we only wanted to make the linear regression of all the measurements, the probabilities, that we didn't want to do anything else. The power must be in the circuit. It's the thing. If not, and we were getting here the Pareto front, but here we added a new step, and I think it's interesting because here before we had the quantum circuit with all the parameters defined by the genetic algorithm. Here we added a new step, which is let's take out let's extract the parameters, and let's do a new optimization of these parameters by using the initial weights that we had in the genetic algorithms. So with this step, what we are doing is to improve the parameters, but avoiding the barren plateaus, because we already have the parameters that are very close to the minima, but they are discrete values, so we probably are not in the minima, but we are very close, so we are gonna go through it, and the structure is the properly one that we obtained from the genetic algorithm. So finally, we had a refining parameters and avoiding barren plateaus with these 2 steps optimization, the first genetic and the second gradient. And this is the circuit that we obtained. Here is the curve, well, the regression of the predicted values and the actual values. And this is the differences that are very close to 0. So it worked, and I was very happy that worked. And this is some dates that we had just as test that worked. And this is the real images, and this is the quantum forecast. As we can see, are very close. And for t plus 20, so it worked properly. Yeah. And yeah.
Thank you for the talk. Are there questions or comments?
Yeah, I have one question. For the data, how you generate your genotypes? I mean,
Yeah, definitely. Yeah, perfect. Uh-huh.
How you translate the data, for example, image data to those?
Yeah. That's okay.
Or in this linear data set, how it's,
Here,
yeah,
for instance? Okay, cool. What's the
how
question?
you generate the genotype here for this nonlinear data?
So, do you? Oh, yeah. So I'm gonna explain it here in the. Okay, maybe not. Yeah, definitely. I prefer the whiteboards than the PowerPoint, to be honest. So first we have the genotype, which is just a binary string, right? Here we have like, well, it's 5 bits. 5 bits. Huh?
First one, you start with a random sequence.
Yeah, exactly. It's completely randomly. It's in fact, it's random randint is the function in Python. So yeah, and then we have here. This is like this circuit. It's okay. It's just 3. In the first approach that we have here. Okay, yeah. In this approach, we only are encoding parameterized rotations. So every single rotation has one of the variables, okay? But in the second approach, when we were implementing the universal gate set, then here we can have also for each axis, we can have fixed rotations. So maybe we have this. Okay, so it's straightforward for the variables, but it depends on the genotype that it's getting. Yeah.
So the synthesis that you found as the optimal synthesis, they are classical.
Yeah.
It's
Yeah.
how do you task, that's like the find the classical that is the idea if your quantum can be smaller than the classical equivalent, but at the end we rescue with a mean because we have a large space.
Yeah.
But here at the end we find that
Yeah.
not-
Yeah, a lot. Yeah.
57. So
Mhm.
why?
I mean,
Task.
that's the thing, I think. Yeah. That this tax, I mean, for instance, tabular data, this thing can be, it's very easy, I think. Well, it's not very easy because it's not linear and there are things, but it's easy. And here, for instance, in the last one that we have, there are more entanglements, and it's because I think it's more difficult, and we need this T-knots because we applied the same things with the same generations and these kind of things, but we need it. We observe that because if we have an individual with 0 C-knots and I don't know error, okay, and 7, okay, cool, 7 cenotes, and the same error, we would take in this. But we are taking, but yeah, so we are taking this one because it's better for the error, to minimize the error. So I think it's, for instance, I didn't say it because I was very fast, because I knew there was a class of chemistry later, but in these problems, for instance, this is very easy to see, the contrast, like the ground and the green is very easy. But in this case, it's not that easy because there are like very different, very different tones of blues. And it's quite difficult to distinguish with the green in some places. So that's why I think it's needed also the entanglement in this place. Yeah, I think so, but
It's our challenge because this prediction of the green presence in 20 days. Of course, there is all this seasonal thing. So I understand that you took a very long series with very
Yeah.
of the seasons,
yeah, exactly.
but since we have seen everything included. But still, how this, I mean, you were showing this Gaussian, this doesn't say much to me. How does this compare with any classical protocol that is on my laptop?
Well, it's a good question. So, I mean, if we compare the classical approaches for these things, I mean, for instance, let me go here. I don't know here where. Okay. Like here, for instance, are the classical models in which we can see that the accuracy on the quantum models are better or the same. But if we go, for instance, for segmentation tasks, there are very huge models and very, like it, are difficult to train because they need more computational time and resources. But there are very good models on the classical ones, like UNet, or for the predictions of time series, we can use autoregressive, we can use LCTMs, recurrent neural networks. There are a lot of models. So, or even the CNNs with LCTMs, which is the model that are most one for image prediction and these things. But the goal is, how can we do it with quantum? No, how can we? How can? So it's yeah, no. I mean, the goal is can we do this task with quantum operators? That's the goal.
Are you including the realistic features of the IBM platform, for instance, or is noise included in your
No,
assessing this whole idea?
yeah, no, it's ideal. Yeah, it's simulation. Yeah. Maybe in the future maybe it will be super cool to test it, but right now it's simulated. Yeah, it's all simulations. Yep.
Yeah, just, can it be the fact that you penalize the use of CNOT that makes the optimization process to avoid them? So
Yeah.
the resulting circuits
Sure.
are classically simulatable.
Yeah, sure.
Due to the fact that you penalize these CNOTs. But if you avoid this penalization, maybe the results you get would be more quantum.
Yeah, definitely, yeah.
Find the structure where there are entanglement gates, but it does not mean that the system is not classical because this is the small system. You see how it scales when you do this.
Penalize them is reasonable, just to say that I think the class, because you can do quantum even if it's not needed. The performance of the games, and then you don't penalize. You just they just penalize themselves.
Exactly.
That can decide anything, or if it handles anyway only with local notations.
Yeah, there are like a lot of ways to see these things. Like we can change a lot of parameters, like removing the CNOT penalization or adding more penalization on these things, or adding more bits for more quantum operators. There are a lot. Like it's not very difficult just to say to change the parameters within the fitness function. Now that it's done, so it's possible to do a lot of experiments with these things. But also something that is very important, I think, it's that since we are penalizing the CNOTs, we can do these things, and we can see we can use this interpretability technique, let's say, now that it's important in the artificial intelligence, the ethics, and to understand the results and interpret the models. If if the models can be less complex, much better. If the models reach a good accuracy, perfect. So if we can understand that this point here is good, here is okay, but here is okay, cool. If we can understand every single point, maybe we can apply this for fraud detection, for instance, and understand which is the problem for one prediction and these kind of things, no? So it's a bit deeper, you know?
How do you decide the number of qubits that you take?
Yeah, that's a good question. I didn't say it because I was running. Yeah. So for the first experiment, for instance, in this one, we started with 6 qubits and 6 layers as maximum, okay? But we only have 2 variables, so why, no? That's a good question. In this case, we were just getting 6 because we wanted to see how it's reducing the model. But the thing that I've been observing when I was doing all the experiments, it's that, and in fact, what I was doing here in the next experiment, I mean, I did it, so okay, cool. Here we are encoding the PCA with just 6 bits, which is 64 dimensions. And these models, have 6 qubits and 11 layers, which is 66. So I did this because I wanted to put all the variables inside of the circuit to be sure that, okay, you have all the information. Now you can do whatever with it, okay? So it's...
Take a picture.
Uh-huh.
Unique, I don't know how many pixels, 3 colors, and then the resolution of the degree of that is either 8 bits, 10 bits, 11, 25 bits, whatever. So are you going to take a whole picture to fit in that? That will be a number of qubits.
No.
Very much. Or are you taking a piece of the, so how you decide what is the piece that you put or what you process at the time?
Okay, yeah, I understand. So in this case, well, this is like the encoding. This is the quantum circuit. This is the like how we extract the information. This is the dimensionality reduction of the model. We add just 64 dimensions because it was more or less good for this. And I was trying, and I was like, 64 is okay. If I have more, if I have less number of components, I don't have the same variance. So that's why. But for sure, if you need more, like here, there is another bit that you can use, for instance, and it will be 128. So you can have more with no problem. I mean.
You get a reasonable result, I mean, you get with the left, or you start the other one and start with the big one, and then if you over-dimension that, you see that there is gates that are not needed or whatever, or ones that are not interested.
Yeah, in fact, I didn't say it, but in fact, here in the models, if we look at the models, we have less variables than the ones that we have from the images. Why? Because it's also feature selection model. Exactly. No, this is, I mean, yeah. Like I'm gonna put it here. So we have the PCA with the number of components, And then from here, we are obtaining a vector with the PC with lambda1, lambda2, lambda n. Yeah. So the variance is getting more in this one than this one. So the model is detecting this and is getting the best ones. So it's like the dual optimization, let's say.
Created the number of say, if you take 7 cubes, means that you are considering several eigenvalues of the pixel component. And now it's not that direct.
It's not direct. It's not direct. Because if we have 6 qubits, in this case, and we have 64, and times layers, and we have 64 dimensions, okay? Okay, every single dimension has a place in the model, but in the evolution, it's probably replaced by a fixed rotation, one of the variables. So we are probably, and we are doing it, we are getting the first eigenvalues of the principal components with more variance and eliminating the last ones. I don't know if it's a question.
Say that you want to consider 10 principal components,
Uh-huh.
then you might need 10 qubits. You want to consider the accuracy of the equation to 20, you might need 20 qubits.
No,
So
it's not. No, it's not. The number of components is not related to the number of qubits. The number of qubits, you define it, and the goal is that the matrix M times N, it's higher than the number of components, let's say. This is the goal. This is the goal.
they are called more sophisticated units.
Mhm. Just testing and adding here more, and that's all.
So you can add n, don't need to increase n.
Yeah, exactly. Yeah, exactly. Like this can be, I mean, you can try and you can put 7, 8, whatever, but the goal is that this rule must be defined. But it's not the qubits. It's not the qubits. It's the whole matrix. Yeah. Yeah, because if it's the qubits, then the variant plateaus is here again, and we have the problem. Well, it's not this, but yeah. And it takes forever when you are training the models if you have a lot of qubits and the symbols. Yeah.
I was asking it before, exactly why, because there is a penalty lesson. Do you have any questions? Comments? No?
If it's too much the number of layers, then you will have metals, right?
Well, it's a number of qubits. Ah, okay. But it's in a number of qubits, no layers.
But instead of like working with deep circuits, then they started if it's block.
Yeah, yeah. Yeah, so for more qubits, you have to have more depth to actually face.
Yes.
Or more. Mm-hmm. Yeah, that's why we are trying to reduce the complexity and reduce all the layers with identities. So that's why we're trying to do these things. And yeah. So that's all. Problem.